Hey, what's up, guys? This is Sheng here. Actually, I want to briefly talk about today's daily challenge problem, which is number 316. Remove duplicate letters. I think this is a very interesting problem. Okay, so you're given like a string. You need to remove the duplicate letters so that every letter appears only once, and you're not only you're not only asked to remove the duplicate letters, but you need to remove that letters in a way such the remaining string should be the smallest in the lexicographic order among all the possible results. And okay, and this problem is the same as the question is same as this one. This one's just a smallest subsequence of distinct characters is equivalent to that one. So basically, you have a B, C, A, and B here. As you guys can see here, we can remove B, C, uh, A, B, and C. So for this string here, since B and C, right, we have two B and two C, which means that we can remove one B and one C. But which one to remove, right? So in this case, we should remove a B and C because the A is smaller than B and C. So basically, we're trying to remove anything that's before A, right? Because A is smaller than that. So that A, B, C is the smallest one. And then the second question is C, B, A, C, D, C, B, C. So this one is a more complicated one. So basically, as you guys can see, we have three C's. We have 1, 2, and 3. 3C, 2B, and 1D and 1A. So for A and D, we cannot remove them, right? But for the C and B here, right? So we can remove C and B here because we have some B and C later on here. So we have B and C, and then here we have for C here we can remove the between this two C here, right? So we want to remove the C right here because if we remove C here, I mean we will have D here, right? So basically D is greater than C, right? So D is greater than C. That's why we want to keep the C that's before D here, and we'll remove C here. So B is we cannot remove it because B there's no more B left, right? So C here we can also remove this C because we already have a C in the string here. Okay, cool. So and the length of this S is like 10 to the power of 4. Okay. Mm, you know, every time when you see like this string problem, it's asking you to find the smallest or biggest thing, And one way of doing this, I think I'm not sure if we can solve this one with the with dynamic programming. Mm, Probably yes, we have a but but for this problem, a better way of solving this is just using a greedy uh, solution, which means that greedy plus a stack. So if you guys and this one requires you a bit of observations. Since I think some of you may have already noticed that, right? So the strategy of the removal of the removing is like, I mean, if the current letter if the current letter has as for example, if we're at A here, right, the reason we can remove C and B is because we have C and B later on here, right? Later uh, appears more than one times in the string here, so that when we have a A here, we can simply remove the C here. So what I mean is that we have a stack here, right? So the stack is this. So first time we have C, okay? We have C, and then we have a B, okay? And every time when we have a new letters comes in, right? We compare this letter with the item on the top of the stack. Okay, and if this letter has some remaining if the counter for this one is still greater than 0, then we know, okay, we can simply remove it because, by removing this one, we can, because the current one, let's say the current one is B, right? So the current one is B. So by removing this C here, we have a B at the beginning of the string, which will give us like a smaller lexical graphic order string here. So that's why when we have a B here, we're going to remove C here, right? And now same thing for A, right? So when A comes, right, we check, okay, so is A smaller than the top one of the stack? Yes, it is. And we also need to check if the B has the counter of B is greater than than 0 or greater than 1, because if there's no such B here, if there's no B here, then we cannot remove B here, because if we remove it, then so the string will be missing a letter, right? But since in our case, as you guys can see here, so the B counter is 2 here, right? So we can safely remove this one. So now we have A here. Now the next one is C, right? So we have C here, but C is greater than A. So which means that we cannot remove C, because if we remove A here, the string will become bigger, right? So, and then the next one is D. Okay, so D is the same one. So D is like, it's also greater than the one on the top of the stack. Okay, and then we have B here. So B, yeah, so B, as you guys can see, so B is smaller than D, is also smaller than C. But the problem is that, uh, sorry. But the problem is that, okay, we're only comparing with the top one. But the problem is that, the D does not have any remaining letters for us to pick, because D only has one here, right? So that so that's why we cannot remove D. Assuming if we have a D here, right? And then when we have a B here, we can simply remove it because we know the BD is smaller than the D and B. But in this case, since we don't have any additional D here later on, so that's why we cannot remove this D here. And then the last one is it's C, right? So when C comes in, um, yes, it's already in this stack here, right? So it's already here. So that's why we can simply skip that. Yeah, I think that's the basic idea here, right? I mean, so the implementation, I mean, as long as you can make this observation, right? I mean, the implementation should be pretty straightforward enough, right? And so we'll need a stack, right? So the stack is this, and yeah, and then we simply do this, right? We just do a for character in as here, right? And then mm, so yeah, so first thing first, we need to count the appearance of each of the letters. That's why we use like a built-in Python built-in function we call counter, which will give us like a dictionary, right? Which key is where key is the string, the letter, and the value is the appearances, the times that the letter appears in the string. So here, every time when we have a letters here, we simply do a counter, do a count. We do a count of this C minus one first, right? So that's what. So we decrease it by one, so that later on we can check, right? So later on when we have a different numbers here, we can check. Okay, so if this letter has anything left later on, right? Otherwise, we cannot keep track of that, right? Because we have to remove the ones we have seen so far. So that's the first thing here, right? So and then we need to remove we'll check first one if the stack is not empty and the current letter is smaller than the ones on the top, right? So the ones on the top, okay, so that's that. So and if the counter of the stack on the top is greater than 0, then we can simply remove it, right? So we can simply remove the stack dot pop. Okay, and so once we remove that, right, we can simply add this thing, append this C here to the stack, and in the end, we can simply return the we can just return the string that we joined uh, by joining the stack. Okay, join stack. Okay. Oh, and one more thing here is that so we haven't uh, handled this the last C here. So the C here, even though the C so because for the last C here, since it's already appeared in the stack here, right? So we need to simply skip that. Okay. So which means that if the C is in stack, uh, we simply continue. Okay. But one thing I think we can improve here is that uh, to search this string in the stack, I think it's O of n time, right? So that's what we can do here. We can do have a set here. Okay, we do a scene set here. Instead of searching in the list here, we search in the scene here. Okay, so for that, and we need to maintain this. Besides the stack here, we also need to maintain this scene the set here. So which means here scene dot add c. And when we remove it, we also need to remove it. Okay, so we can simply, we have a removed here, right? Removed, and then we can also remove the scene dot add. Sorry, yeah, add removed. Yeah. So this is just like a little some additional improvement so that we can keep our time complexity to O of n, right? So here we have O of n, and so here is O1, but we have a while loop, but as you guys can see, we will only, since we are keeping, since we keep popping the letters from the stack here, so in total, we will only be doing this like this pop uh, n times, right? So, oh, so let's try to run the code for, uh, uh, did I do anything wrong here? Let's see here. Hmm, count. We have A here, B and C. Hmm. Stack is that, scene is this. So if this is in scene, we continue. As removed. Hmm. Oh, here. So, so when we pop the things out, instead of add, we need to remove, right? So we remove the scenes from the scene set. Okay. So let's run the code. Okay. So now it's accepted. Let's try to submit it. All right. Cool. So it's also accepted. Yeah. So basically, that's pretty much it is for this problem. It's I think it's a good medium level problem. The only things you guys need to be careful is that not careful to remember is the to get the smallest, right? We either use a dynamic programming or we use a binary search, but in this case it's not applicable, or the greedy, right? So for the greedy, you always can get the smallest or the maximum. And for this problem, greedy is a proper way of solving it, right? Basically, uh, you have to basically you need to make some observations. Basically, you need to see how can you uh, greedily remove the letters we don't need, right? And then we can keep the ones uh, that we cannot remove, and we remove everything we can remove, following this kind of strategy. Okay, yeah, and time complexity is O of n because here this is n here, and here you can think it as an O1 here because the stack is not we will so each of the ladder will only be removed once in the stack. So here is like also a O of in total is O of n. So here's O of n, right? And yeah, and the time space complexity is also O of n, right? Of this. Cool. I think that's it for this problem. Yeah, thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.